Good evening, everyone. My name is Matt Ritter, and before I start, I want to give a quick thanks to Sarah and Adam, who wrangled up all the extra chairs that we needed this evening. I've never had a talk get so big so fast, and I just want to assure you that I'm not in the least bit completely terrified.
So,
let's...
Matt, can you turn up the, or maybe put it closer to your face? It's not picking up that well. Okay.
Great. Now I can hear two of me. Models. They get all the attention, whether in machine learning or in fashion photography. It's easy to think that when you look at a photo that the model is all that matters. But in reality, to get anything done, you need to have a whole variety of people, including stylists, photographers, even the people who book the travel and deal with the catering. And collectively, at least, these roles are at least as important as the model themselves. And I'd argue that these skill sets not only are relevant, but unlike models, they never go out of fashion. So tonight, we're going to be focusing on all of these surrounding technologies, the things that enable a full innovation pipeline. But let's just take a moment to ask who, what, and why. So I'm Matt Ritter. I'm a lead on the data science team at Athena Health. I've started considering myself more of a machine learning engineer, and I'll be talking about all the reasons for that in this conversation, because I think that the full system is really critical, and I try to increasingly think more broadly about the entire data pipeline. In this talk, as Adam noted, I'll be talking and focusing on neural networks and natural language processing, both of which I focus on professionally. But I think that much of it should be general to all sorts of machine learning pipeline workflows. Obviously, my views are not those of my employer. I have not, for example, asked our PR department whether we have a stance on models. I also just want to take a quick moment to give a shout out to anyone who lives west of Boston or Camberville. If you ever want to get in touch and talk data, my contact information for you and everyone is at the end of this slide deck, which of course will be shared broadly. So it's exciting to be here with all these new friends. So what are we going to be doing? How are we going to be doing it a little differently? So my alma mater, Olin College, is really into the concept of spiral learning, which is the idea that of course you can't learn something just the first time you see it. So how do you design a curriculum that lets you touch the same concepts again and again and again until you're comfortable with it? So with that in mind, we're actually going to go through the pipeline twice tonight. First at the meta level. So we're going to use a lot of analogies, and we're going to try to get you comfortable with the idea of what we're trying to achieve at each stage in the pipeline. And then obviously at the object level. So what does the code look like? What does the output of the code look like? And we'll be using one of several technologies, kind of the middle of the road ones. But of course, any of these can be swapped out for whatever you happen to prefer, whatever your organization uses. This is designed to be an overview, so even the code and output examples can be supplemented by the really fantastic stuff that you can find online, O'Reilly and GitHub and every place like that. So I'm really just going to be focusing on the stumbling block concepts in this talk. And why are we doing this? Innovation doesn't come in light bulb moments. The Wright brothers didn't just sketch an airplane on a piece of paper, build it to spec, and take off. Their biggest engineering achievements might have been their wind tunnel instrumentation or their engine test stand. Similarly, Bell Labs, which produced dozens of innovations, including the transistor, had many brilliant people like Claude Shannon, but also 13,000 employees, many of whom were technicians who helped implement the ideas that the PhDs came up with. And finally, Edison. Edison was absurd. He was the most prolific patented inventor in history. He invented the light bulb, and he couldn't even count how many experiments he had to run to create it. Modern historians are estimating between 5,000 and 10,000 experiments, but he could get away with that because he had an invention machine, right? He had a literal factory full of workers to churn through inventions and ideas. you need an invention factory. You have brilliant modeling ideas, but you don't have 13,000 employees. You don't have a literal factory. But you, I, all of us are blessed to be in an industry and age where the automation allows us to build our own factory. So let's get going. Again, we'll start in the abstract. Here's the problem. You are at a small company. Your manager didn't realize that Silicon Valley is supposed to be a joke. They came over to you and said, the Silicon Valley TV show, they have this app called Hot Dog, Not Hot Dog. It seems to be able to identify. It's very accurate. I mean, like, very, very hot dog looking shoe. We get all these comments all the time about various foods, and we need a hot dog, not hot dog for text. So you find yourself hour after hour hand labeling data, and it is getting old pretty fast. So you decide to build a data pipeline. And, can we turn down the lights a little bit? Is there any way to turn, no, we cannot turn down the lights a little bit.
Turn all the lights off. They'll go off actually at 7, by the way, the heads up.
Oh, great. All right, so quick, I'm assuming no, but can people read this word?
No.
Can people read this word? Yes. All right, thank you from the front for confirmation and affirmation, but it sounds like we're gonna try turning the lights off. Okay, is this a little better?
Yeah.
Okay, great. Perfect amount of light, thank you.
Okay, just don't go to sleep, guys.
Yeah. All right, so this diagram, this data flow diagram, you're gonna see this a bunch, so I wanna take just a moment to explain it to you. First thing to keep in mind, this is the data flow for training, not for predicting. So once the model's in production, your programmers have to think about how the model and how the data actually flows in the application. That's a completely separate presentation. Next, it obviously flows from left to right, starting with a query. And I'll make a quick note. Those of you who work with production systems might be cringing just a little bit that I'm saying query from production. That's a little dangerous, and often you want to be querying from backups or data warehouses or something like that. Here and throughout the presentation, I'm going to go with the simplest possible way. Do not copy paste this into your company's code, and if you do, don't hold me liable. And then finally, so we've got the extraction is the step name, and then up here is the common file types that come out of that step. I find it useful to just think about how it becomes tangible after you do this operation. So querying is quite a bit like going to the supermarket. You have all this stuff, data, food, what have you, and you are collecting it from around, from various tables, various shelves. And of course, you don't just run to the back of the supermarket, grab one item, bring it to the checkout counter, check it out, run to the back of the supermarket, grab a different one, etc. You persist it, right? You create a little space, a temporary space, that you can hold the data together and work with it as one chunk. And so that's what we're going to be doing here and throughout this data pipeline. We're going to pull data from each step, pull it together, get it into a good format for the next step, and then move on. So in your hot dog, not hot dog example, you run the query overnight, and you end up with a nice chunk of data sitting in your computer. Let's move on to tokenization and labeling. So like groceries, comments can come in a variety of sizes, right? So one person might say, it was great. Another person might copy paste Harry Potter into your comment box because the internet, right? So your GPU needs a consistent shape. So you need to get things into a bite-sized standardized format to feed to your hungry, hungry GPU. Now, this was a big mental breakthrough for me, and so it's worth a moment of digression to get into. So I, as a data scientist, you as data scientists, anyone who's working extensively with neural networks lives professionally in a symbiotic relationship with this thing called a GPU. And it behooves them to understand what on earth it is. So the first question, of course, is what does GPU even stand for? And the answer to that is simple. That's a graphics processing unit. So that's in contrast, or more generally, in addition to a central processing unit, which is sort of the core of anything that you'd consider a conventional computer. And what makes a graphics processing unit special is that it can do simple array operations very, very rapidly in massive parallel. And they were originally developed for graphics, as the name would imply, but at some point, some neural network researcher got their hands on it and realized that it can dramatically speed up the training. And in fact, almost all of the deep neural network revolution that we've seen in the last few years was sparked by that insight and that realization that we can use the progressively more powerful GPUs at our disposal to do truly extraordinary things. And so to your role as a data scientist, as someone who uses GPUs, your job is to set things up for the GPU. Every single point of this data pipeline that we're going to be walking through is designed to get things into the format that the GPU can work with. And that's because the GPU is 10 times, 100 times, maybe 1,000 times more powerful than anything else that you've got access to. So you're kind of like this guy. It doesn't matter how often this guy goes to the gym. He could get as strong as humanly possible, and it wouldn't matter. His whole job is to set things up so that this powerful symbiotic relationship that he has can use its strength to get the job done. All right, let's return to the pipeline. So something else that confused me for a long time is how can you start with words and pass it into a GPU that requires numbers? And the answer to that is word2vec. And again, I'm using one solution. There's a few other similar ones, but this conceptual explanation will apply to all of them. So if you have a word like cheeseburger, like how can you turn it into a number that is meaningful in any sort of way? And the answer is that it's not just one number, it's a vector. In this case, a two-dimensional vector. And the exact numbers don't really matter. What does matter is that the vector for cheeseburger is very similar to the vector for hamburger. They're very near each other when you plot them on 2 dimensions. Bok choy, though also delicious, is very far because by almost any conceptual measure, they're quite distinct foods. And you might wonder, what's the value of that? The amazing thing, and this is truly mind-blowing, is you can actually do math with these concepts. So you can take a yam, subtract out the orange color, add in the white color, and get a vector that is very similar to that for potato. You can take a grill, subtract out summer, add winter, get oven, right? You often grill in the summer and heat food with an oven in the winter. And so you might be asking at this point, like, okay, I understand what it does, but how do you get this magical thing? And the answer is that would be its own presentation. So we are just going to have to leave it for that, leave it at that for now. And let's move on to designing a model. So as promised, I'm not going to get too deeply into recurrent neural network or how convolutions work or any of those details. Other people have done it really well across the internet, and I'm trying to focus on the underserved aspects of the data science workflow. But there are a few considerations when you're designing your model. An engineering consultant friend of mine once sat me down and told me what he tells all of his clients. Good, fast, cheap. Pick 2. And that's been an important reminder that you have to make in any engineering profession, and that certainly includes data engineering. So good has a number of nuanced potential meanings when you're talking about a model. So accuracy is probably the first term that comes to mind. And that's perfectly valid, but maybe a false positive is much worse than a false negative, or vice versa. So you want to use a slightly different measure of model performance. Fast, so when does your model hit production? When are you done with this project? But if you're designing Nimble data pipelines like I'm describing tonight, you won't just hit production once. You'll get there with a minimum viable product, see how that performs in the wild, and iterate as fast as you can. So that also has a little bit of nuance. And then cheap is actually at least 2 different concepts. This is owing to the cloud revolution. So one of the things that's enabled us to do such extraordinary with deep learning in the last few years is that you can rent an extremely powerful machine for a relatively brief period of time. So it wouldn't make sense for most companies to own as many GPUs as Amazon does, but to use them for a few hours at a time is well worth the cost. But that said, it is a cost and it does add up. So that's one of the things you need to consider as you're designing your model, which will necessarily influence how long your model takes to train and therefore how expensive it is. And then finally, your own time. You're valuable. If you're not working on tweaking a model, trying to get out the last little bit of performance, then you could have been doing something else. And maybe that would have brought more value to the business or more value to yourself. So the cheap is a multifaceted concept as well. So you've got a model. You've got maybe even multiple ideas. And you're going to start training. And the thing that I want you to remember about training is that training is the first time that you get a good look at these models. And if they're not looking good, get them out of there. Like, there's so many. There's no reason to get too attached to your first great idea or your second great idea or whatever. You will have more ideas, and if during training something's not looking good, kill it and move on. All right, so you've got a few models. You're zeroing in on the absolute optimum that you want to take to production. And now it's time for sort of your final optimization. So you've got, in this case, two parameters. Maybe one is batch size, another is the number of densely connected layers that you're trying to use, whatever. And then vertical is performance. Again, we talked about how nuanced that can be, but if you can boil it down to one number. And that's where you start to explore the multidimensional manifold and try to get to the best possible place within the time and money constraints that you've already identified. Finally, you get to deploy to production. You take your best model, you get it out there, and this is what it looks like. It's actually kind of underwhelming. But on the upside, you can stop spending hours reviewing hot dog comments. You can still spend hours reviewing hot dog comments. So we just blazed through that. And hopefully that was exciting, but probably it still feels a little fuzzy, especially for some of those stages. So let's go through it again, and let's do it a little bit more detail to solidify your understanding. All right, so we'll start again at extraction. So many organizations store their data in SQL databases, relational databases, which means that you'll probably end up using SQL at some point in your project. And the queries can be very simple. So in this case, we're selecting the text and the label from production again, from the comments. But we're doing something that I really want to highlight here. And this is a really important part of my argument that the entire pipeline needs to be nimble, needs to be part of your agile process. So we're having a filter here. We're saying that no spam. So imagine you have a different system to detect spam, and you're just not going to train on that. That's fine. That's totally defensible. But you're probably making that decision before you've trained a whole model, right? Before you've seen any results. So remember that this is a design decision. Just like any tweaking of a hyperparameter, or just like changing your model architecture. And as you iterate, remember that this is something you can play with. Maybe you could add more filters. And so once you do that, you make your call, you get out results. And so what I'm showing you here is an example of JSON-L. So JSON is basically dictionaries in Python or hashes in some other language, where you have a key and you have a value. So here's the value, and then you've got another key, you've got a value. JSON-L is simply a bunch of JSONs stacked on top of each other. And you can go many thousands deep. The advantage is that it's all text, so you could open it with your favorite text editor. You can take the head on your command line. You can do whatever you want. The downside is that it's pretty verbose, right? So this key, which is much longer than the value, is repeated every single time. So if you're pulling on the order of 10 million data points, this can get a little bit overwhelming, both from a disk perspective and from a processing time perspective. So now let's talk about tokenization and labeling again. So again, our goal here is to digest this for that hungry GPU. So you start with one of these text things, and then you do what's called tokenization. And the simplest way to think about tokenization is just splitting into different words. So everywhere that there's a space, put in a different word in the list. But there are a few design decisions here as well. So I'll start with the end. Hot dogs has an exclamation point, which I've omitted here. I've decided that for our use case, exclamation points are not relevant. But maybe you're doing sentiment analysis, in which case exclamation points might want to be their own token. So it's not exactly one token per word anymore. Or maybe the fact that it's attached to dogs is important. So this is actually, you're going to make it a different token than dogs without an exclamation point. These are the sorts of design decisions you have to make all the way up and down the pipeline. Another one is taking this date and using a regular expression to recognize it as a date and tokenizing it not as the full string, but as the tag date. And this can be really powerful if you don't care exactly what date it is. You just care that there is a date in that sentence. And this can dramatically reduce the dimensionality of what you're ultimately working with, and therefore allow you to build more complex models because you're using less verbose data. And then finally, the label. So in this case, there's just two classes, whether it is related to hot dogs or not related to hot dogs. But I write it out like this, all verbose, because in many cases, you're going to have 3 classes, 4 classes, 10,000 classes. It could be every username that's ever commented, and you're trying to sort new ones. And so your labeling decision is actually pretty fundamental to what sort of problem you're solving. And it can change quite a bit based on that. All right, so let's move on to embedding. This again was that kind of magical thing, and I'm still not going to explain it, but but at least we can look in a little bit more detail. So we tokenized in the last step. We have this list of words, but we still need to turn them into numbers for that GPU. The beauty and the reason that I can get away without explaining how a word2vec really works is that you can just download one from any of a variety of pre-trained websites. And at first, I was really nervous to open it up because I thought it must be some super complex structure to capture the nuance of all these words and how they relate to each other. But it's actually literally just a text file. And the structure is pretty simple. On the left-hand side is the word itself. And then over on the right-hand side is the vector. And since we are trying to keep it simple, I'm using 2-dimensional vectors. You'd almost never do that in real life. You'd want to use something actually several orders of magnitude bigger. That's how you can really capture the sorts of nuance that I'll let you talk about, do with this conceptual math with colors and stuff. But for this example, just remember that 8 became 0.3 and 0.8, and we're putting it there as a little vector. And so then you just repeat throughout the tokenization. So 8 became 0.3, 0.8, on gets its own token, gets its own vector, date does, great, hot. Oops, no, sorry. Great does not get its own vector. And the reason for that is that it doesn't exist in the trained word2vec. So in most situations, great would be something you would expect to see in any broadly trained word2vec. But you have to remember, this is the sort of company that thinks that Silicon Valley is a documentary. They don't get called great very often. So, so you'll see this happen at times, and that's fine. It doesn't have to bring everything to a halt. You just put 0, 0 in as the vector, and of course it can be as many zeros as you're using as your dimension. Obviously, if you're starting to get a majority 0, 0, or even a very hefty fraction, you might want to reconsider whether this approach is going to work for you. But you can get away with maybe a little bit more than you think. The other thing you can do, because remember those Amazon boxes, you need everything to be exactly the same size, you can do what's called padding, which is that if you decide you want the tokenized lists to be length 7, you just add zeros to the end until it is. So in this case, there's 6 real tokens, and you just add one more 0, 0 on the end there. If it had been 8 tokens long, you just chop off a token. If it had been 700 tokens long, you just chop off all but 7 of those tokens. And so that lets you get that consistent size that you need. Again, this is a design decision, and design decisions require trade-offs. So you are, of course, throwing away information if you chop off tokens. If you use something that's way too long, your model might get a little confused about all those zeros. And so this number, both these numbers, the 7 and the 2, are again things that you're going to want to tweak and play with as you iterate on your pipeline. All right. So let's take a look at the model again. So again, we're not going to get into too many details, but pursuant to our goal of making these models super interchangeable, you really just want to think of them as a black box, or if you're on a black background, a white box. That takes, this is the thing that we were just making before. These are your model parameters. So these are the things that people mostly focus on, and they're very important too. And then these are the weights, of course. So you just start with randomly initialized weights. And all three of those together produce an output. Again, this is during the training process, so this is not a label. So it doesn't know for sure whether the sentence that was encapsulated here has the essence of hot dog, but it's at this point pretty sure. And then of course this purple line represents the backpropagation process that will move these weights in the right direction slowly but almost surely. And the details of that, again, are better explained elsewhere. Let's move on to monitoring training. So this is TensorBoard. It is the interface for training if you're using TensorFlow or Keras with the TensorFlow backend. There's lots going on, but it does give you some really good information. And if you sort of learn what to look for, it's pretty manageable. So let's take a look at this blue, it's not quite a line, but this blue squiggle. It is going down. That's good. So it's basically measuring the cross-entry, so that's how wrong you are, very broadly speaking. And over time, as your model trains, it gets less and less wrong. So that output that we saw 2 slides ago is getting closer and closer to the actual label of 1 for hot dog and 0 for not hot dog. So as long as it's getting better, you'd be inclined to keep that training going. But you can see it's bottoming out. It's not going to get all the way down there. And you need to make a judgment call. Is this likely to be a contender to be your best model? And that can be really tricky, actually. You can spend a lot of time thinking about how to determine whether a model has promise after a few tens of minutes of training. And again, pursuant to your goal of cycling through these things as fast as possible, you're going to be doing a lot of cutting off of training. And so getting good at that is important. Finally, you've gotten towards the end, you have a few models that you think are doing pretty well, and you need to start thinking a little bit higher level. So that graph that I showed you, that was just for one model training. It really zoomed in on how things were going throughout the training process. And this is an interface that can let you look across models. So you can see here there's a model ID, just all randomly generated IDs here. And you can compare the score on the test set. What's critical about the test set is that you did no training on that test set. So you pulled it out really early on. You didn't let any of the models touch it, and then you use it consistently to compare the models against each other. So it's supposed to be your best validation about how the real world is going to work. Then you've got a whole bunch of your hyperparameters and the other things that you set. It's easy to think that this is actually kind of simple because all these numbers are nice and tidy in their little boxes. But what really happens in real life is that you change the model architecture, and then a bunch of those numbers aren't valid. Or maybe you expand the model and you need more numbers. And that's how you get model names like this, right? So this is not exactly what I've ever written before, but it's, I didn't want to embarrass myself too much, but so it's like 12 months, this is how much data that you had. So again, way back to that first step, it matters. If I had 24 months, if I reached back an additional year, that's more data, generally good. But maybe we had a policy change, and we allowed foreign languages in the last year. So suddenly you've got twice as much English, but not the other foreign languages represented. That's a design decision. Maybe that's what you want, maybe it's not. 6 epochs, so that's basically how long did you let it train. Bug fix. You can have models that have bugs that output a number. Sometimes that number looks fantastic. That is literally the worst. Oh wait, other bug fix, 17. So yeah, so it can spin out of control is what I'm trying to say. So it's important to have a good system that where you can look at all of these things together and really make informed decisions about which ones you want to take to production. One thing that I'll note is that most everything else that I've showed you has been a fairly standardized tool and one that I've used myself. the leaderboard concept, so looking across these models, for whatever reason, I've seen less coalescing in the industry around how to do that. And so this is one that I've not actually used because we built our own at work. But it's from Future Gadget Lab, and it looks pretty nice. So give it a go. Let me know how you think. Again, we have a self, and that would be a great discussion topic sometime. All right. So we've done all this work. We've done it twice. Thank you for staying with me. We now have a nimble, cohesive system that can be optimized all the way up and down the data pipeline and give you dozens of little wins, 1% from the extraction, 1% from the embedding, and just slowly and consistently optimize the entire pipeline to improve the performance of the final production model. So I'm going to wrap with a quote from a senior scientist at Bell Labs. And I think Bell Labs had an even deeper impact than you might know. It's obviously where the transistor happened, a lot of information theory, but it also invented some of the first satellites. Its success stretched for decades, and I think they really hit on something. And so what this researcher said is that out of 14 people at Bell Labs, only one was the idea person, the math on the chalkboard kind of person. And that's because pursuing an idea takes so much more work, and building a system to effectively pursue an idea is absolutely critical to bringing anything to fruition in the real world. So maybe you'll never have 13 lab assistants, but I want to underline how incredibly fortunate we are to work in this space. We can use automation to build our own invention factories, and I hope that this inspires you to take at least one step towards this goal. Thank you. Great, I think we have some time for questions. Is there a mic or should we?
Yeah.
Who has a question? Who's closer?
Hi, so you described the whole pipeline building from scratch to building your first model or deploying your first model, but there is also an aspect of maintaining the model management. What do you think about that, or how you want to tell us what some idea how you want to do that, how you want to approach that problem, or after 3 months, how you want to make sure that it still perform the same way as you first get into production? Thank you.
That is a phenomenal question and an absolutely important concept that you should give a talk about next week. No, you're right. All of these concepts come into play again, and I'd say additional ones that people should be aware of are alerting. So you don't want to be checking on your model performance every day. You're going to get tired of it. You're going to stop doing it. So set an alert that sends you an email, sends you a Slack message, however your organization works, when the model performance slips or dips in any sort of way. And then additionally, making sure that you've got multiple people at the organization who know how the model works. Again, I think if there's one thing you take away from this presentation, it's that you should design for scalability, design for everyone to be able to understand, get in there, make a change, make it better. And making it better sometimes includes fixing what is bad.
First of all, thank you. That was very entertaining and awesome. I have a question because I've fallen into this model naming thing that you showed a lot. You have one model and then you distribute it across multiple GPUs, and then the name change, and you have all these other bugs, and then you introduce more data. And you mentioned the leaderboard thing. Does that allow you to add notes or other aspects that are not easily captured in a structured data format? You mentioned that you guys use your own. I'm just kind of curious what is available to people that don't have whatever you guys have access to.
Sure. Well, I don't want to imply that what we have access to is particularly amazing. It absolutely gets the job done. It does have what you're describing, though. So that said, it's not too sophisticated. It's just a free text field where you are encouraged to write everything you can think of that might be unique about this approach. And we actually had different sub-teams within my organization have handled it differently at different times. But one thing that we definitely have is the Git hash. So use Git or whatever version control works for you, and be pretty consistent about checking in every significant change. And so push comes to shove, it's annoying, it's awkward. You can reload what things look like then and check how that parameter was defined. We've had other teams that have actually they've done their very best to split all of the pre-processing decisions that I talked about into exactly one file. It's a super long and ugly file. But then they actually load all of that into the metadata. So you'd have boxes like that, but then one of them would have this giant scroll thing where you can just look at the code itself. And again, it's terrible, but at least you know what's in there.
Thank you for the presentation. One of your examples for the hot dog query was, I believe, it was the bratwurst, but misspelled, pun, clever. It strikes me that that would have failed the embedding because it is a misspelling. It is an uncommon thing. Do you come across examples where, in your work, that you're attempting to do something and you're foiled by the messiness of it all? And what strategies do you have to think about and deal with those?
Great question. So yeah, as Adam mentioned, in my work we work with FATS data, which means that we work with optical character recognition, which means that although I think our system is about as good as you can get, there absolutely are eyes become ones or what have you. So we do a few things to try to get around that. One is sometimes we use character level stuff. So for all this, we're breaking it into words. If you break it down by character, upside is that the space of separate characters, separate tokens that you might have to worry about in a character level embedding is tons smaller, right? So 26 lowercase letters, 26 uppercase letters, scattering of special characters, and ignore like the copyright symbol or whatever. So that can give you the signal that's in there, but then of course your tokenized thing is super long, and it's up to your model to deal with that. Other teams have done things like stemming, where you take words that are, sitting, sit, sat, become one word. If they're misspelled, that may or may not work, depending on how sophisticated that stemmer is. And then other teams have actually implemented entire kind of lookup mechanisms to handle situations where you're one or two characters off. And that's actually very much its own presentation as well.
Highly engineered, then.
Absolutely, yeah. It requires its own database. It requires its own, yeah, it's huge.
There's, as I walk over the mic, there's also a Python library that I don't remember the name of the guy's name. It starts with L. That's like Liechtenstein distance.
Oh, yep.
That you can, if you have a word that's not in the dictionary, you can figure out what word is closest to it by just running like Python Liechtenstein word thing word, and it'll tell you something like that.
It's also Fuzzy Wuzzy.
That's the
Fuzzy, right, and also well named. Yeah, Fuzzy Wuzzy can be a little slow, and again, like all of this, it so depends on your application. When I say it's slow, it's still sub-second, but in some cases you need sub-millisecond.
Hi, thanks for a really helpful presentation. So my question is, entity resolution, so these situations, I don't know how much this comes up with what you do, but knowing what something is, especially if it's like abbreviated, so is it International Business Machines, is it IBM? Okay, now we have millions of them, now what do we do? Is that something that you can speak to with your approach?
Sure, it's very important, and we absolutely do it. I'm trying to sort of connect it to this. It would be, so something else that you could do with this sort of situation. So imagine that you successfully solved whether there is a hot dog happening, but someone wants to know where the hot dog is happening, right? And then, like you say, you might care about the difference between hot dog and ballpark Frank or whatever. You're wearing a Boston Red Sox hat. What's it called? Fenway Frank. Right, so in some sense that's entity resolution, and like you say, company names, people names, all those things are very important. I would say that it is also a very complex thing, and I'm not a super expert at it, but what you want to do in general is use the first round system to gather as much information about that entity. So not just the characters themselves, because the exact same collection of characters can mean two different things. Many of us share a full name with at least one other person in the world. But if your date of birth is in there, even just your year of birth will probably do it. That's where you can start to actually get a hit. And so using a system, and it gets complex pretty fast, to pull as much information relevant to that entity, which is tough when they have many entities, in together to give to your entity resolution system, do that lookup, give a confidence score, pull it back, and then potentially even continue with your first system.
How do you decide when to stop optimizing your pipeline? And assuming, for instance, your metrics are great on whatever your application is trying to do, how important is it for the whole pipeline to run X times faster?
Yeah, that's a great question. I'd say the frustrating but true answer is it depends. But to give you something a little bit more useful, I guess the next step, more detailed and useful, is more than you think. Right? So I think it's easy to get it working once. Maybe it takes 24 hours. Like, that's not at all impossible. And you're like, oh, that was terrible, but it's done. I'm only gonna iterate on the model, and like the rest of it that it takes so long is totally fine. It doesn't matter. I obviously don't know exactly what context you're going to find yourself in when you're making this decision, but more often than you think, at least in my experience, you do end up having to go back to that first step. You do want to change that filter in that initial SQL query, and you have to run everything downstream. And so, I'm generally an advocate of getting those things running quickly, or at least, and remember the 4 different things you can optimize. If you can't get it running quickly in terms of calendar time, right, like if it still takes 24 hours, at least the amount of developer time, and preferably AWS time, can be minimized so that you just kick it off, you set a calendar reminder to check in on it 24 hours later.